Welcome to Maths with EJD. We're still on numerical analysis, right? We are now considering interpolations and approximations. And under that, we've been looking at polynomial interpolation. Polynomial interpolation. So, and there are two forms here. We have the Lagrange form, the Lagrange form, and we have the Newton form. The Newton form, which is also known as the Newton divided differences, if you like, say form, Newton form, basically. So in the last video, we had considered the Lagrange form. So our attention turns to the Newton divided differences form in this situation. So we're talking about Newton divided differences. Okay. So Newton's divided differences let's see what that is about. Newton's divided difference interpolation is a method for constructing and an interpolating polynomial using divided differences. Okay, it is particularly useful when data points are not equally spaced. So the other one, the Lagrange polynomial form, guess that would be better for equally spaced data points. But here this is particularly useful when data points are not equally spaced. The interpolating polynomial is given in the Newton form, as what we have here. We have Pn of x equals f of x naught plus f of x naught plus f of x naught x1 multiplied by x minus x naught. So it's actually a very long formula. So that goes, and then okay, I'll just bring it down, plus f of x naught x1 x2. It may look a bit confusing, but never mind, I'm going to explain. So all of this into x minus x naught into x minus x1. So that's the next level. So that can go on, so plus everything until we get to f of x naught x1 up to xn, and then we have all that multiplied by x minus x naught. You can already see the pattern, x minus x1 up to x minus xn minus 1. Okay, So that's how this goes. Now the formula may look somehow, but we'll explain. An example will make it very clear. Okay, so that's what the Newton divided difference formula looks like. But of course, what are those components now for clarity's sake? So where f of xi, whether it's x naught or whatever, is the same thing as f of xi is the value, that's the value of the function, the value of the function at xi. So whatever function you're given, I mean, the value of the function you're going to get at xi, then you have f of xi, comma, xi plus 1. And that is this is the first order divided difference, calculated as f of xi, comma, xi plus 1, which is equal to f of xi plus 1 minus f of xi divided by xi plus 1 minus xi. So that's an expression right there that we're going to be using a lot. So that's the first order divided difference. And that's not all. We still have other forms. We have f of xi plus 1, xi plus 2. And this is the second order divided difference, calculated recursively as f of xi plus 1, xi plus 2 equals f of xi plus 1, comma, xi plus 2 minus f of xi plus 1 all over xi plus 2 minus xi. So we have all this. And that's good, and so on, right? And so on. And so on for higher order divided differences. I mean, the formula may look complicated, but the deal is you can do these things from your table, as I'm going to show later on. I mean, we can do it using the formulas. We can also do it from the table directly, which I may be able to show as we go on. So let's take an example with the same points we used for the Lagrange polynomial form. So we have this, given the data points, x naught, y naught, which is 1, 2, then x1, y1, which is 3, 4, and x2, y2, which is now 4, 3. So we begin to take the steps. Step one, we compute divided differences. Well, using the formulas, first of all, I mean, here we know all the x's we have. It's from x naught to x2, x1, x naught to x2. So we have x naught, x1, x2. So to do that now, we need f of x naught, x1, and that means we have f of x1 minus f of x naught. I think this is even straightforward. This is x1 minus x naught, and this is equal to f of x1 So, what this simply means, if you look at all of these things, so this is f of x naught, because y naught is f of x naught. So this is x naught, this is f of x naught. This is x1, and this is f of x1. This is x2, this is x2, right? And this is f of, oh, okay, I should be talking about the values themselves. So 4 is x2 and 3 is f of x2. Okay, so that's the idea. So f of x1 here is 4. F of x1 is 4. So that's 4 minus f of x naught is 2. So that's 4 minus 2 all over x1 minus x naught. So x1 is 3, x naught is 1. So we have 3 minus 1. So that means that, okay, I can even do that in a straight line. So I can save some space. So that's f of x1, 4, f of x naught, 2, then all over x1, 3, x naught, 1. So that is 2 over 2, and that is equal to 1. So we see that f of x naught, x1 is equal to 1. Okay, so that's equal to 1. Taking note, so we take note of that. So then we can go, so you keep going, you take them in pairs until all the pairs are exhausted. So we have f of x naught, x1. So we also need f of x1, x2. So that means we have f of x2 minus f of x1 divided by x2 minus x1. This is where the divided difference idea comes up. So f of x2 here is 3. That's the 3 up here. F of x2 is 3, and f of x1 is 4. So all over x2 minus x1. x2 is 4, and x1 is 3. So that's 4 minus 3. So we have 4 minus 3. So that means we have that to be minus 1 over 1, and that is simply minus 1. Now, f of x1, comma x2 is equal to minus 1. So we take note of this also. So we are done with all the first order. So first order divided difference. That's what we have done so far. I should say that actually. This is, we have the first order divided differences. Divided differences. So if we have like x3, x3, y3 again, then we would need to still do x2, x3. So, but now we just have x0, x1, x1, x2, because we have 3 data points. So with that done, we move on to the second order divided difference. So we have second order divided difference. Second order divided difference. Only one of that because we have just 3 data points. So again, we come over and say, here we need f of x0, x1, x2. And that is the same thing as f of x1, x2, okay, minus f of x0, x1. Interestingly, we've got this before now. So all of this will now be over the biggest x and the smallest x. So that will be x2 minus x0, okay? So that means we have f of x1, x2, we got that to be minus 1. Then f of, so this is f of x1, x2, and we have f of x0, x1. That's 1. So we have minus 1, minus 1, all over x2 minus x0. x2 is 4, x0 is 1. So that's 4 minus 1, and that is equal to minus 2 over 3. And that's what that is. So we say f of x0, x1, x2 is equal to minus 2 over 3. So we take note of that. I promised I was going to also do it using a table. So let's look at how we can, instead of using all these things, we can actually do it from a table, like I said. So again, we have, say you have, okay, I think I like to do I, right? So this is I. Then after I, we have xi, and then we have yi. Okay. So, and we have just three data points. So we have 0, 1, and 2. 0, 1, 2. So, x naught, y naught, x naught, y naught is 1, 2. So this is 1, 2. Then we have the next one is 3, 4, and then we have 4, 3. 1, 2, 3, 4, 4, 3. 1, 2, 3, 4, 4, 3. Yeah. Okay, so with this now, we can do the first order differences. So first, okay, let me extend the table. First, so first order differences, first order differences. We know that is simply, so we have two of those. That will be f of x1 minus f of x naught. So this is like, okay, I guess we can, okay, we can shift it down, right? We can, or we can do it, we can, trying to see if nice way of doing this. Okay, so let's just shift it down. So first order difference is simply going to be f of x1 minus f of x naught. So that will be 4 minus 2 divided by 3 minus 1. And that is why we have 2 over 2. And the answer is 1. That's exactly what we got up here, right? Then we move on to the next first order difference. So that will be, so, you take this pair first, then you move on to this pair. So the next one is now just going to be, okay, I guess I want to color code for easier understanding. So now we have 3 minus 4. That'll be 3 minus 4 all over 4 minus 3. 4 minus 3. And that is minus 1 over 1. And that is minus 1. That's how we got it. So instead of using all the formulas, you can just master the table thing. So then that can move us to the second order difference. Second order difference. Now, because we have two first order differences, we are just going to have one second order difference. If we have three second order first order differences, we're going to have two second order differences. So that means that we're also going to need a third order difference, if you have more data points. So the more the data points we have, interesting. If we have three data points, go as far as second order difference. If we have five data points, we move as far as the fourth order difference. So until you get one thing at the end of the day. So here now you're simply just going to have so, um, so if you look at this, right, this whole thing covered uh 0 and 1, and this whole thing covered 1 and 2. So if you are doing the next order difference now, so you can then look at this whole thing like everything together like this for the second order difference. So for the second order difference, it's easy to just move on and you just say that now this is going to be this value you have here, that's your f of x1, x2. So that will be minus 1 minus f of x naught, x1. So we have minus 1 minus 1. So this minus 1 minus this one all over the biggest value, I mean the highest value in the range, that's f of x1. I mean f of x2, that's 4 minus f of x1, that's 3. And that's why this is minus 2 over 3. So if we have maybe the next value now, then you now need to do whatever you have here minus what you have here. And then you have to, so in that case, now maybe it's extending to something else, and then there's a value here. So in that case, now it's not going to be whatever you have down here minus what you have here divided by whatever value you have here minus these three, you know. If you write down the formula, it will be clear, but you can also do it from the table. And that's why I've taken the pain to make this explanation. Okay. So once you calculate the divided difference, that's the crux of this whole formula. So it's because that's why it's called the divided difference method. So the first step is to calculate to compute divided differences. That's step one. And we have done for first order and second order. So the next thing we want to do is that's step two, right? Step two. So step two, we now need to substitute. Okay. Step two, we now construct the Newton polynomial. Construct the Newton polynomial. And we already know what the formula looks like. So in this case, we have, we can only go as far as 2, because of this value here, P2 of x. So whatever that ends up as, if you start from 0, that's the order of the polynomial you're going to have. So you're going to have a second order polynomial because we have 3 data points. If we have four data points, you're going to have third order polynomial. If you have 10 data points, you're going to have ninth order polynomial. So here, this is P2 of x equals P2 of x equals f of x naught plus f of x naught x1 multiplied by x minus x naught plus f of x naught x1 x2 multiplied by x minus x naught into x minus x1. And that's as far as that goes. Now you discover this is the raw formula. This is the the f of x naught, and then this is f of x naught x1 multiplied by x minus x naught. This is f of x naught x1 x2 multiplied by this, and that's the order in which that goes. So then we can say that p2 of x again is equal to f of x naught is y naught basically. So that's y naught, which is 2. So we have our 2 here plus f of x naught x1, f of x naught x1. We already computed that. So, as you know, this is okay. Well, following the formula, right? We already got all that. F of x naught x1. Okay, what happened there? Okay, get it. Yeah, f of x naught x1 is 1. Okay. F of x naught x1 is 1. So this one is 1. So we have 1 into x minus x naught. Our x naught is this one right here. So that's 1 into x minus 1. Then plus f of x naught x1 x2. That's minus 2 over 3 here, which is this same one now. Okay. So we have minus 2 over 3. Now that's into x minus x naught. X naught is 1. X minus x2. Again, x2, x naught is 1. X2 is 4. X2 is 4. No, x2. And what's happening here? Minus 2 over 3. X minus 1. Okay, x minus x1. So x1 is actually 3. X1 is 3. X1 is this 3. Okay. So we have this is 3 now. Okay, so that's the expression we need. So we have P2 of x equals 2 plus x minus 1 minus 2 over 3 into, if we can expand this straight, so x times x, that's x squared, minus x minus 3, that's minus 4x, minus 1 times minus 3, that's plus 3. That's a fast way to go about that. So P2 of x is equal to 2 plus x, we can expand, right? So 2 plus x minus 1 minus 2 over 3 x squared plus 8 over 3 x, minus and minus, then minus 6. 3 cancels 3, so we can just say minus 2, right? Minus 2. So now we can tidy things up according to the coefficient. So we have just minus 2 over 3 x squared for 2 over 3. For x squared. So minus 2 over 3 x squared. Then for x, we have here, the coefficient of x is 1 here. And here it's 8 over 3 x. And for the constant, we can say plus Okay, I mean, we can just even go straight. Uh, this is 2 minus 1, 1. Okay, 2 minus 1, that's 1. Then 1 minus 2, that's simply minus 1. Okay, let me just do this. So we have P2 of x equals minus 2 over 3 x squared. So here the LCM is 3. If you say this is 1 over 1, so this is 3 plus 8x minus 1. So finally, P2 of x is equal to minus 2 over 3x squared plus 11 over 3x minus 1. This is exactly what we got with Lagrange formula. Exactly what we got with Lagrange formula. So once you do it right, that's what you get. So just like I said, okay, we can conclude, right? So we can say, thus, the interpolating polynomial for the given data points, for the given data points 1, 2, 3, 4, 4, 3, is the second order polynomial P2 of x equals minus 2 over 3 x squared plus 11 over 3x minus 1. So that's the formula. And then we can say that this polynomial can now be used to estimate function values at any x. In fact, if I have a practice question for you to be in that line, so practice question, I'm still going to show the Python code briefly. Practice questions. So evaluate P2 of x at 1, x equals minus 3, 2, x equals 5. Okay, so that means just substitute this into that. Let me give you something that is fractional in nature, let's see what that looks like. X equals 1 over 7. Okay, so it means we need p of minus 3, p of 5, and p of 1 over 7. And to show the Python code quickly, let's see what that looks like. We're talking about Newton divided difference now. Newton divided difference is polynomial. So this is what that looks like. If we show the line numbers, okay. So I mean here you declare the points in lines 4 to 6. Then the divided difference, how it works, is defined there. So you can study that to understand. And this is the declaration of the formula itself. And then the given data points, you call them up here. Then the divided difference is happening here. Then the Newton polynomial. So please study that and you understand. So by the time you run this, that's minus 2 over 3, right? So minus 2 over 3 is the same thing as minus 0.66667 x squared plus 11 over 3 is 3.66667 x minus 1.0. And that's how that simply works, okay? So don't forget the practice question, just to try your hands on that. Then you can just pick random points and try out these methods I've explained so far. Just pick any point. So that comes in very useful. If you have a set of points and you want to get a function to represent them. So these two polynomial interpolations can be really useful for you. We are going to learn other methods as we go on. I think in the next video, I'll be talking about spline functions and cubic splines, okay? And that provides a kind of very smooth way of doing, representing data, smoothing out data or something like that. Okay. So if you have subscribed, thank you so much for that. If you haven't, please go ahead and do that and hit the notification bell so you can at least get alerted each time a new video is released. In the comment section, do these practice questions and let me see your answers in the comment section. Also, let me know how helpful these videos are and let me know if there's a problem you'd like me to solve or a topic you'd like me to teach. Like and share also so that more people can have access to this great learning. Till I come your way again, keep doing maths right. Bye.